Okay, so this is just see better, just help you see better. We're going to move on to help me understand sort of the quality of my code. Help me measure. If you can't measure something, it isn't real. Okay, so first thing, we talked about formatting and styles. Okay, what you might do is establish a set of style standards for your organization. Okay, they can be all kinds of rules. You can insist that paragraphs be named. You can insist you have documentation in places. One rule you might insist on is that if you're writing in COBOL and you have a series of if statements, you don't want to write them like this. You want to write them as what's called an evaluate statement, which is a more structured form of this. So a tool that can go through and find anything that looks like this in the code and say, hey, that's wrong, and diagnose it, that's not good style. Okay, you can get that, encourage the programmers to switch to a better style, and that makes it easier for the next guy down the road. You're in this for the long haul. You have to maintain your system forever. Any little incremental change you can make over time is good for you. Because our engine is capable of taking an analysis result that is detecting that that's wrong, okay, and using it to drive a transformation, we could actually use the engine to say, well, when we find this, why don't we just do that to the code? Why do I have to make the programmer do it? So if you, as long as you're clear about what the rules are, if it looks like this and that's wrong, how would you reshape it? You can explain to our engine, well, why don't you reshape it like this? That means you can not only get good style, but the programmer doesn't have to be involved in that loop. He can go on and do more productive things for you. Okay, dead code. Big systems, long time, lots of changes to the business rules, to the guys working on it, to intentions. Everybody has dead code. Okay? But if you have dead code in your system and a new guy doesn't know where it is, he's going to spend his time looking at the dead code, wasting your resources. What you'd like to do is find the dead code, okay, and eliminate it. Just take it out of your system. It's not doing you any good. Okay? Zombie code. So zombies, the Walking Dead. Okay, if you actually look at big systems that evolved over time, they have sections which execute business logic, which is no longer relevant. The corporation has changed directions and we're not going to do this anymore. So in our example, we have a special thing that we do when the account numbers are small. So when we started up the bank, we had small account numbers. We gave the first 2,000 bank accounts very special properties. Okay, and so we have a special piece of logic for them. That's long gone. We have 1 million accounts now. But you still have this piece of logic in your code. But nobody has account numbers like that anymore. It's not a question from the application engineer. Does he have to maintain this code? Well, he doesn't know. Okay, he has no way of telling. What you'd like to be able to do is to go through and say, hey, I've seen this condition in the code. I go talk to the managers, okay, about whether this can ever happen. So I discover it's no longer possible for this to ever happen in my program. And you want the application engineer to say, that can never occur. And because that can never occur, all this other logics in between can't possibly happen. You can apply standard dead code elimination techniques to remove it. So this is a way of getting rid of the cruft in your code. All right. People build big systems by copying parts that almost do what they want and modifying them. Okay, I had payroll for this group of people. I need payroll for another group of people. Let me steal the whole payroll subsystem and carve it up. I get 2 payroll subsystems. They're almost alike. I've got twice the maintenance load. What I'd really like to have is I'd like to figure out what their commonality is and maintain that. Okay, and separate out the differences and maintain that. Okay, so this is an engine whose job it is to look for duplicate pieces of code. So you can imagine 1 million lines of code. This is a piece of code which is a bubble sort. It's a really lousy sort, very slow. Okay, you'd like to have a tool that goes through and says, I found this bubble sort piece of logic. It's been copied 3 times. It's been modified in all 3 places because the guy had to change to make it slightly different. Okay, and they're all essentially an implementation of this. And what you'd like to do is, first of all, just identify those patches so that if somebody makes a change here, you go like, hey, if you change this one, you ought to change the duplicates because otherwise you've got a replicated bug. Right. Or actually go through and extract it. Pull this piece of abstraction out to someplace and replace the calls, okay, with the actual invocations of that thing. And now when you have a problem, you fix that, you got all 3 of them. Right? Systems tend to be 15 to 20% redundant. Okay, so 15 to 20% of your programmer's time is spent looking at redundant code. That's a lot of engineering money. Okay, here are examples of real COBOL codes, real COBOL clones. So these are taken from the California Community College District, which is trying to keep track of what classes they have in colleges and in districts. And they've copied the code. Okay, we applied our tool to it and found these 2 blocks of code that look, well, frankly, almost identical. And they've been patched in these 2 places. So the tool actually understands, okay, that these things are different in these places. And it can put, whoops, well, we didn't have time for it. I have an example, if you want to see it offline, of abstracting that and making copy lives out of it. Okay, this is all static analysis. Give the tool your source code, let it think about the source code, and produce answers. There's dynamic analysis, where you measure property systems as it runs. A really interesting one has to do with test coverage. I've got a large system. I made a bunch of changes. I want to ship it. If it's wrong, my company dies. Do I ship it? How do you make that decision in a rational way? Well, first you need tests. That's already a sore spot because we don't have many tests. It's a whole different topic. Okay, but let's assume you have tests. So you got one test. You run the one test, it passes. You going to ship the system? No. Okay, how about 2? How about 3? What number do you stop at? Okay, it's wrong to ask about the number of tests. What you want to ask is how much of your code has been tested. So you need a way to measure which part of the code has been executed by tests so that when the test passed, you could say 90% of my code has been exercised by the tests. Okay, now I can feel good about shipping my system. So what a test coverage tool does is it instruments the source code, watches it as it runs, okay, collects the execution data, collates all that stuff, and puts it up in a display where both programmers and managers can see it. So it draws a picture like this and says, that piece of code there, that red line, red means stop, it never got run. So you can't trust it. It produces management reports that basically give summaries, statistics, this much has been tested in this system, that much in that subsystem, folds it up on systems. So this is a way of measuring how well your code has been tested and gives you a rational method for deciding whether you should ship. Okay, so we've talked about what I think are small tools, things that make people individually more productive or make it easier to measure things. I want to talk about sort of massive exercises and talk about some experiences there. The tools that I've shown you so far are a little standard in the sense you can say, I could probably build a tool like that for any system you have. These tools are not like that. Okay? Anybody that has a large system and carries out a massive change wants to do something that's completely custom to him. The input set of technologies he has is unique to him. The output set of technologies you'd like to target to is completely unique to him. So you can't get an off-the-shelf tool to do this. So what I'm going to show you here are not examples of tools, okay, but the examples of sort of results of tools and kind of how they work, just to give you a sense of what that's like. Okay, so we talked a bit about why manual migrations fail. Okay, mostly they fail because engineers are slow. Okay, an application engineer can convert 100 lines of code a day. You have 20 million lines of code. Do the arithmetic. It's bad news. Okay, you're talking 200 man-years of effort. Well, you got a team of 20, that's 10 elapsed man-years. You got a team of 200, it's 1 elapsed man-year, but we're going to get the budget. Okay, you can't get people to do that effectively. It's way too expensive. Farm it out to India and use the Mumbai method. We talked about why that one doesn't work. Okay, you can try that. So they're not good at this. And they miss details. If they get the code wrong, God help you if you ship the system. Okay, there's a second problem. You got these guys working on this system. Okay, you got another team doing the migration. You have intense competition between these two teams. There's one team that wants to keep the existing application alive and running because management insists that it keep evolving. It's got to run the business today. You got the migration team trying to build new code, and they're trying to do it by looking at the old code and hand coding things. And if the old code is changing, it makes them crazy because they can never catch up. Right? And so they keep saying to the development team, stop developing, and the application team says, we don't care about you guys, management says we have to do this. Okay, you end up with an incredible tug of war. Right? There's a scope creep problem. Nobody can resist fiddling with it as it goes by. Let's add this feature, let's add that feature, let's add the other feature. Okay? As a consequence, it's very hard for the new system to ever catch the old one, because even if it catches up with the functionality, okay, the new stuff isn't implemented right, and it's still not ready to run. There's a last problem. This is kind of an interesting one. User training shock on switchover. Okay? We talked to Washington State in the U.S. They have a licensing division for driver's licenses. They have 4,000 operators around the state that sit on green screens and take in your name and your phone number and all the stuff required to put in the license. They wanted to change their system over to a new modern system, and there was a question like, let's have a great brand new GUI with flashy stuff. And the problem is they have 4,000 operators out there that know how the old system works, including Control-Alt-Click-Shift F3, okay, to get to entering the field name. And if what you do is screw those people up, you'll have a revolt on your hands. And your system may fail, not because the technology is no good, but because the user community won't accept it. Okay. All right. So what you'd like to do is get a translator to translate that application the way it is and preserve all of its business rules and all of its properties, okay, so that nobody's surprised by the answer. Because your problem when you're doing a migration is to get rid of the technology you don't want, not to fiddle with anything else.